COMSOL Multi-Physics Lecture 8, Part 2, Transient Thermal Analysis. And first of all, we load the software. And then run the COMSOL in live link mode instead of dock mode. So I'll choose live link and toggle it on so I can link software SolidWorks with COMSOL. Now I'll open COMSOL interface in another interface. So I open both softwares and connect them with live link. So now I'll run a 3D solid heat transfer problem. And within solid heat transfer problem, there are two modules. The first one is steady state. The second one is transient thermal analysis. And I'll go with time dependent, which is the transient thermal analysis. And now, first of all, I'll load the geometry from SolidWorks. So this is the first step, that I load geometry or the part, 3D part from SolidWorks. And the second step is the material. And I'll choose material from the library. Aluminum alloy 6063, apply. And it is very important that material will be connected or linked with geometry. You always have to notice that the geometry is properly connected or linked to material property. And both 6061 and 6063 are often used for heat sinks in computer. So this is the second step, material. The third step, I'll make a mesh finer and build the mesh. For the fourth step, since it is a transient thermal analysis, initial temperature is very important. So I'll change the initial temperature to 25 degrees for the whole body. So this is important for transient thermal analysis. For steady state, it is not important, but for transient thermal analysis, the initial temperature will affect the result. And then I'll enter a loading and boundary condition for step 4. So in heat flux, I'll define overall heat transfer rate on the bottom surface. So this is to simulate a heat emission from a CPU underneath. So I'll make it 28 watts heat source on this surface. So make sure that the surface is connected to this heat source. So this is the loading. And then the boundary condition, I also use heat flux, but this time it is convection. For the convection coefficient, I'll make it 10 watt meter square K. And this is a coefficient for air on stagnant condition. In other words, it is a still air. The air does not move. It is a stagnant air. And the ambient temperature or the environment temperature will be 25 degrees C. So, and make sure that this property will be applied to all the boundary except for the heating surface. So make sure that all the surfaces that get in contact with air are selected. So I use all boundaries and deselect the underneath surface. So all these blue surfaces are defined as heat dissipating or heat convection surface with a coefficient of 10 and a temperature of 25 degrees. So now I have finished with the preprocessors, and now before I run the study, I need to define the time range and time step in transient thermal analysis. So it is important that in transient thermal analysis, you define the total time and time steps to replace the original and then compute. So in steady state thermal analysis, you don't have to define a time range because the time goes to infinity and the system become equilibrium. But for transient thermal analysis, you always have to define the end time and the beginning time and also the time steps, and the system will calculate step by step. So we have about 80 steps, and this is the result. And for the temperature, the software gives me a very weird color, so I'll rather use the rainbow light color. This is a more comfortable color scheme for me because the colder temperature will show in blue and the hotter surface will be red, and I'll be more comfortable with this color scheme. So I choose rainbow light instead of the original thermal light. So I go back to rainbow light, and I like this color scheme better. But now the most important thing is that we will detect the temperature at this spot. So I'll go to derived values and define a point evaluation on this point and evaluate. And the software gives me the temperature from time 0, which is 25 degrees, to a temperature of 101 degrees C. So it is a correct result. And we can draw the curve. You can see here that at about 1800 second time, the system had already reached thermal equilibrium and the temperature will not change. And also, when the system become homogeneous or thermal equilibrium, the temperature at the spot that we indicate, the temperature will be 393 degree K or 101 degrees C, and the value is exactly the same as the temperature for steady state thermal analysis. So you can see here that actually in a thermal system, the temperature rise from 25 degrees C and then increase with time, and then after a time interval it will reach thermal equilibrium and enter a steady state mode. So actually the steady state temperature is the temperature here, that when the transient system become thermal equilibrium.